Okay, so in this video, I'm gonna introduce the second interpretations for the PCA method 2. Okay, so actually you can think the second way to interpret the principal continuum is to find the direction W that maximize the sample variance of the projected data. In other words, when we project the data down, so we want to find the vector so that the variation of this projected data, the variance is largest. So this is our W. So in this case, our original space, we have two features, x1 and x2. And given each W, we can predict, for any given W, we can project each data point onto this vector W by using that formula, right? So by using the X inner product with W, right? And times W too, times W. So this gives us all the points here. And we can calculate the variance of each projection, and we want to pick the W which gives the largest variance. So that's the interpretation. So the algorithm is to find the algorithm. Second way to derive this is find W. Maximize variance of the projected data x1 tilde, x2 tilde, xn tilde. Okay, so how do we calculate this variance? Which means we have the sample variance. The formula is given by so xi multiply the, because remember this is our centered point, so we normalize this and we square it. This gives us the variance because it's centerized x. Okay, and actually this can be written, this can be rewrite as 1 over n x times W. This is a vector now, so norm square divided by W, this vector square, which can also be written as 1 over n W transpose W. Okay, so W transpose X W. Okay, think about what quantity, what kind of W gonna maximize this value. Actually, by the eigenvalue decomposition, the vector so for eigenvector with largest eigenvalue lambda d, okay, Vd. So we have this W. We have this quantity equals to V so we can think this is x omega x x v vd transpose x vd, okay, vd transpose vd, okay. So remember since this is eigenvector, right, this eigenvector, so this quantity is equals to lambda d square vd transpose vd, okay, vd transpose vd, okay, and this can cancel this. Actually, if for the eigenvector w, this is the largest eigenvalue square, okay. So therefore, actually, and the general proof is for the eigenvectors, it attains maximum at 1 over n, okay. And if for the general vector, actually you can write as a linear combination of the eigenvectors, then we can prove the similar things. So first, again, so this is a sketch of the proof. For detailed proof, you can check the elements of the statistic learning book. So this implies VD is the first component. Principal component. Okay, so the eigenvector with corresponding to the largest eigenvalue is the first principal component. So that's the second method to derive, to think about this principal component. Actually, there is another interpretation here. Principal component analysis method 3. So this will give you all the same solution, but it give you different interpretations. Maybe let me show you one more picture here. Okay, actually the third method, you can think this is just find a W. Find a W that minimize the mean squared projection distance. Okay, as you can see that for each of the possible, for all possible W, we have the projection points. Okay, as we can see, the mean squared distance of this projection distance, which is minimized all this small projection bar here, that W give us the the idea is similar to the mean squared regression. So we minimize each of the projection distance. Okay, so that's the idea. So, but it's very similar similar to the least square linear regression line, but there is one important difference. In the linear regression, we minimize the horizontal distance between the predicted value and the true value y, right? But in this principal component analysis, we minimize the projection distance. So that's the differences between the least square regression and the principal component analysis. Okay, so I will give you two picture here. So that's a third interpretation. So the third way to find the principal component, the space, is to find the W that minimize the mean square distance between the xi minus the projected points. Okay, for every data point. So we can actually rewrite this as summation I from 1 to n xi minus, so we know how to find this projection points, right? It's just xi inner product with w divided by the norm of the w square times w. We normalize it and then square. And this can be rewritten as I from 1 to n xi square minus xi inner product with the w, okay, divided by normal w and square. Okay, actually this is, you can write down this as a constant minus the variance of the projection distance, n times the variance of projected points. Okay, I'm not gonna give you the detailed proof here because it takes too much time. So that's third interpretations of the principal component space.